In chapter 2, we evaluated limits. So to appreciate what we're going to learn, which is called L'Hopital's rule, go back to what we used to know about simplifying limits. We're going to do these 3 problems. Just sort of remember 3 possibilities when we're simplifying limit expressions. So you should pause the video here and try these 3 problems. That first problem, no problem, because we simply substituted in 7 for x, and we simplify. There's nothing that went wrong that prevented us from finding that limit. The second 2 problems, though, we had a problem. One was a 0 over 0 problem, and the next was a infinity over infinity problem, which those expressions aren't defined. So we needed to do some other math, and we talked about some algebra ways to do that, to simplify those expressions. L'Hopital's rule is another method we can use to simplify limit expressions that originally result in 0 over 0 or infinity divided by infinity. So here's what L'Hopital's rule says. If you're trying to find the limit as x approaches a of f of x over g of x, so right now it only works for quotient problems, and you find that f of a and g of a are both equal to 0, then you're going to have a 0 over 0 problem. L'Hopital's rule says you can actually find f prime of a and g prime of a and report that quotient instead. So try that middle example. We're going to use L'Hopital's rule. If I want to substitute in -2 for x, I'm going to get 4 minus 4, 0, over -2 plus 2, 0. So instead, I'm going to find the derivative. This is L'Hopital's rule tells me this is going to be equal to the limit as x approaches -2 of f prime, so the derivative of the top, 2x. And in the denominator, the derivative of x plus 2 is 1. Now when I make that substitution in, -2 in for x, I simply get -4 over 1, -4. Should be the same answer that you got when you did that middle problem up at the top. At this point, it's common for me to hear a complaint from students, why didn't you teach us L'Hopital's rule back when we were learning about limits? Because it's so much easier than all that other crazy algebra we did to simplify limits. So in my defense, let me call to your attention that back when we were learning about limits, which we needed in order to understand derivatives, you didn't know how to take derivatives yet. You hadn't even actually heard of what a derivative was. That's why we can't teach you L'Hopital's rule back when you first learn about limits, because it requires that you understand how to take derivatives, which you didn't know yet. So we can step this up a notch. L'Hopital's rule has an even stronger form. It has even more forms after this too. But this is the next exciting one, which is, what if you take that derivative of the top and derivative of the bottom, but you still get 0 over 0? Well, L'Hopital's rule says you can repeat the process as long as using substitution was going to give you 0 over 0. You can take the derivative of the top and the bottom again and try again. And if that new expression would produce a 0 over 0, you can take the derivative of the top and the bottom again until you don't have that happen anymore. So watch what happens here. I'm going to take the limit as x approaches 0 of 1 minus cosine x over x squared. So L'Hopital's rule tells me that that's equivalent to the limit as x approaches 0. Oh, I have to stop and check. So let's pretend I stopped and checked. If I substitute 0 into my numerator, I'm going to have 1 minus cosine 0. That's 1 minus 1 makes 0. If I were to substitute 0 in my denominator, I'd have 0 squared, which is 0. So I definitely have a 0 over 0 problem. So L'Hopital's rule, first form, the introductory form, says, oh, well, let me take the derivative of the top and the bottom, and I have a new expression. I'm going to take the limit as that new expression of the new expression as x goes towards 0. So the derivative of my numerator, that's like the derivative of negative cosine of x, is a sine of x. The derivative of my denominator will be 2x. Okay, so now I'm going to try substituting in my 0. The sine of 0 is 0, and 2 times 0 is 0. So even though I already used L'Hopital's rule, I'm still going to have a 0 over 0 problem. Well, the stronger form of L'Hopital's rule says you can keep going. So I can take the derivative of my numerator and denominator again. I'm going to have an equivalent expression, the limit as x goes towards 0. The derivative of sine of x is cosine of x. The derivative of 2x is 2. This time, when I substitute 0 in, I have cosine of 0 divided by 2. Cosine of 0 is 1 divided by 2. Final answer, 1/2. And L'Hopital's rule even works if that that value that I want x to approach is positive or negative infinity. And if I have my numerator and denominator about to evaluate to infinity over infinity or negative infinity over negative infinity. So watch me use L'Hopital's rule on that third example. I'm going to take the limit as x approaches infinity of x squared minus 4 over 3x squared plus 2. L'Hopital's rule tells me that that's equivalent to the limit as x approaches infinity of, oh, well, I should have checked. That's the second time I almost didn't check. It's because I've done this problem before, not because I don't check. But just double check for yourself that if you had substituted in infinity for x, your numerator would evaluate to infinity, your denominator would also evaluate to infinity. So L'Hopital's rule applies. If you checked that and you didn't get 0 over 0 or infinity over infinity, do not try to apply L'Hopital's rule. It doesn't hold. So now I'm going to take the derivative of my numerator, 2x, derivative of my denominator, 6x, and I'm going to try again. If I replace the x in the numerator with infinity, the x in the denominator with infinity, I'm going to have infinity over infinity. L'Hopital's rule works again. I could have simplified that expression too to get 2 over 6, which is 1/3. But notice I can still apply L'Hopital's rule and take one more step. That's going to be the limit as x approaches infinity of 2 over 6, which is 1/3, no matter what x is approaching. Which is the same answer we got when we did that problem using algebra, looking for the term that dominates in the numerator and denominator. Okay, so here are 3 problems that come from released AP tests. You're going to do them using what you know about L'Hopital's rule, or anything that you remember about evaluating limits. So here I want the limit as x approaches a of x squared minus a squared over x to the 4th minus a to the 4th. Notice that when in my head, I stop and I try to replace x with a. I'm going to get a squared minus a squared over a to the 4th minus a to the 4th. I'm going to have a 0 over 0 problem. So L'Hopital's rule tells me that this is equivalent to the limit as x approaches a of derivative of the numerator over derivative of the denominator. So 2x. A is a constant, so the derivative of a negative a squared is 0. X to the 4th, its derivative is 4x cubed. I can replace x with a now, and I get 2a over 4a cubed, which that's 4a cubed. And that simplifies. I have an a in the numerator and an a in the denominator. They cancel, leaves me a squared in the denominator and a 1 over 2a squared. Final answer. This problem is here because sometimes when students first learn L'Hopital's rule, they start to use it everywhere, even in places where it doesn't apply. So this one's here to make sure that you don't try to apply it in some place where it doesn't apply. Notice here, if I substitute 1 in for x in the numerator and 1 in for x in the denominator, I'm going to have the limit as x approaches 1 of 1 over natural log of 1. Well, natural log of 1 is 0. So I do not have what's called an indeterminate form. I do not have a 0 over 0 problem or even an infinity over infinity problem. I have a 1 over 0 problem. 1 over 0 is undefined. This limit does not exist. I can't try to apply L'Hopital's rule because it didn't meet that original criteria, which is I have to have tried to take the limit and had a 0 over 0 problem, or an infinity over infinity problem. This last one here, I'm just going to find the limit as n goes to infinity of 3n cubed minus 5n over n cubed minus n squared plus 1. I do have an infinity over infinity problem there. It's going to be the same as the limit as n goes to infinity of 9n squared over 3n squared. Oops. 9n squared minus 5 over 3n squared minus 4n, which is going to give me another infinity over infinity problem. You can see the pattern that's going to keep going. You can see the term that's going to dominate too. If you still decide that that's the fastest way to do this problem, just know that we will need L'Hopital's rule for some of the other stuff that's coming up in chapter 9. So here, that's the same as the limit as n goes to infinity of 18n over 9n minus 4. You can see where this is headed. That's going to give me an infinity over infinity problem again. So I'm going to have the limit as n goes to infinity of 18 over 9. Which makes 2, but that's not an answer choice. What happened? Oh, got it, because I multiplied wrong. This last guy here should have been 2 times 3 to make 6n. So I'm going to have the limit as n approaches infinity of 18 over 6, which makes 3.